today my aim is to put science into the sort of narrative that we had last time. We're thinking last time about the way in which we think, and of course science is very much the way in which we think too. What I'm trying to do today is to put science into that context. The idea is then to see, I can get it next grade too by looking at you all. Science, of course, is in some ways a very odd activity. Middle, near front. Okay. Science in some ways is a very odd activity. And I think we should see it's not really a very sort of obvious activity in some ways, much less obvious than the kind of emotional activity that we were talking about last time, really. But it's sort of superimposed on it. Science has all sorts of surprises. It has all sorts of surprising things about it. And you remember that last time I was talking about how, the most obvious thing of all, that the Earth doesn't move, has now proved to be wrong. That's pretty odd. And so, when we start looking at it, and then we also got to think about what the definition of science is, and that actually does matter, because it does matter, because language always matters, and the way in which we describe something. And once you've got some way of describing something, then you can sort of go forwards from there. Whereas until you do, it can be very stifling. And so what we're going to do is we'll give you a little bit of a history of where science came from, how it developed, and where we've got to now, at least to an extent. And I've got just a little bit under 2 hours to do it, which you may think is not terribly long to discuss everything in science from about the 6th century BC until the present day, but I'm going to have a go. So, science literally means knowledge. It comes from Latin just simply scio, which means to know. It simply means knowledge. That's all it actually means. It's taken a much more narrow, a narrow and more distinctive form since about the 17th century. I will come back to that, but science as we know it really derives from there. But then the definition became narrower at that point. But what the essence of science is, of course, as always with everything, where it started with the Greeks. Everything started with the Greeks, pretty well. But this time, actually not the most famous of all Greeks, but somebody who is perhaps not necessarily famous for quite the same thing, but he's still quite famous because he predated Plato and Aristotle. And the reason I'm mentioning him is because he made one insight which I think was absolutely vital for the whole progress of science ever since. And that person was somebody you've heard about in relation to triangles. Pythagoras. Now, can you spell Pythagoras? Or should I spell it on my non-whiteboard? That's what I would do normally. I would write it up, but I am actually being a little bit cautious about whether I really should. Pythagoras. 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 I think I got that right. When you sort of think about it and try and think of how it goes, it's a funny spelling that sort of goes out of your head. But anyway, Pythagoras. Why is it Pythagoras? What's special about that? All you know about Pythagoras really is that he thought that 3 squared plus 4 squared made 5 squared, right? He had a right-angled triangle, and the sum of the square on the hypotenuse equals the sum of the squares the square on the hypotenuse equals the sum of the squares on the other two sides, right? You all know that. You should all know that. That's pre-GCSE maths, and you all passed. Mind you, do you know, I discovered what GCSE maths grade C is. I mean, they might just know that 2 plus 2 equals 4, but honestly, I know. Well, my son's doing GCSE at the moment, and I know. It was alarming as to what a grade C consisted of. And he said that, do you know, can you believe this? Do you know that obviously just telling you that. You're looking a bit surprised. You were not told that. No. What were you told the Part1 was? Do you remember? Sorry?
I got all
70%. Well, it is for some of the GCSEs. I don't see it changing. I couldn't believe it. Anyway, that's entirely irrelevant. I couldn't believe it. You all know though. Of Pythagoras' theorem of geometry. I mean, it's a nice bit of geometry. But what Pythagoras was saying is actually much more profound than that. Obviously, it's a useful little theorem if you're interested in that kind of thing. But Pythagoras did something else. Or at least the Pythagoras and the Pythagoreans, as they became known as followers. And they had sort of, various lifestyle choices as well. That would really go for the present day. We all have more lifestyle choices. No, these days we're all into lifestyle choices. And obviously all of them are good. All lifestyle choices are good. You know that today as well, don't you? But the Pythagoreans had slightly peculiar lifestyle choices, as some people do today, and but they were very keen on this idea, the fundamental idea, which underlies science, that mathematics. He was fundamentally a mathematician. Mathematics underlies the world, underlies the working of the world, and that you can actually. The great thing about maths, I mean, this is one of the things about the GCSE business. I mean, maths to me is right or it's wrong. There isn't an intermediate, really. If you get it right, you get it right. And if you, I know, okay, there may be some places, but I mean, 2 + 2 really does equal 4. It doesn't equal 5, and it doesn't equal 3. And so, you have that sort of basis where maths, and if you say that the world is underlain by mathematical principles, you are giving it a quite different look from what you might otherwise give it, in that it gives it a sense that we might actually be able to understand it. And I think that's the fundamental idea. You may feel that maths is not your best subject. Maybe it is. For quite a lot of you, maybe it isn't. But the point is that maths is only applied logic. It's just logic. And if we can understand the world mathematically, it means we can understand it logically, which means that somehow it follows certain patterns. And it means that you can get certain rules out, which then can be applied elsewhere. And obviously the Pythagorean theorem is a sort of is just a very minor exemplar, really, of that idea. That the world makes sense, some sort of a sense. It's the beginning of rationality, really, being rational. And after all, rational is based on the idea of ratios, isn't it? That's what the whole word means. And the idea is that by working out certain things like that, you can make predictions about another thing which will work, and you can then test it, and you find it actually does follow the same rules. So you've got these mathematical rules. He fundamentally put mathematics into the world. And the point of it, that math, it's applied logic, it's just logical, and it works. And fundamentally, nearly all these early scientists regarded themselves first and foremost as mathematicians. They were interested in maths and physics, which is kind of applied maths. And physics, even now, has become even more obviously applied maths than it used to be. But Pythagoras really did make an extraordinarily big change, because he sort of made it so that the Earth could be understood. The way in which the world works might be able to be understood, or at least parts of it. And then science, in many ways, built on that idea. And of course, then the other Greeks came along, and we had a number of other Greeks, and most prominently Aristotle, I mentioned last time. Aristotle was so prominent. I mean, he was one of the greatest intellects the world has ever known, and I think nobody would dispute that. So much so that his, and his followers, of course, his ideas managed to dominate the world, at least in, well, no, it dominated the world. It really did dominate the world. I mean, leaving religion aside for the moment, it dominated the world for 2,000 years. And fundamentally, Aristotle was he was the ground, he was the base on which everybody based their ideas. And he obviously developed this from Pythagoras and started putting everything into its sort of rational place as he saw it. He was very much the complete materialist. He actually really particularly looked at the world and what was in it and tried to make sense of it. He made all sense of a great number of things. Of course it wasn't only him. He tends to be the figurehead that we think of, but there were various others as well. In fact, following him, the Greek medical man, Galen, who actually worked for the Romans, but he was Greek, he was a kind of Aristotle of medicine. He fundamentally thought about how the body worked, and his medicine was his medicinal books and tracts became the kind of ground on which medicine was built, in just the same way Aristotle's was the ground on which so much else was built in terms of what I suppose we would broadly call science was built. So it wasn't obviously just Aristotle, although I don't want to completely cover you with names, as it were. No point in that. So anyway, Aristotle then he wrote tracts about almost everything. He wrote tracts about astronomy, about biology, obviously, chains of being, and that sort of thing. And he sort of set this groundwork. And he and the Greeks generally, of course, they wandered around. Anybody been to Athens? Have you seen the Agora, seen the Acropolis? Who's been to Athens? You have. You're the only one. None of the rest of you have been to Athens. Oh, do go. I think. Sorry?
I'll definitely go there with the whole £5
I can't quite hear, but don't worry about it. I should take a field trip from here, shouldn't I? Part of this module, obviously, I have to go to Athens. Athens is wonderful. Because so much of it is actually still there, even though they use the Parthenon as a gunpowder dump, which is not a terribly clever place to everything to store in one of the most beautiful buildings in the world. If you go up to the Acropolis and look at the Parthenon, it seems to almost float above Athens. It's just one. I think it's probably the single most remarkable building I've ever seen, it's just astonishing in the way. You know how it's built. It's all built towards mathematical principles. You know that how the pillars aren't straight, for instance. They slightly taper to give you the sense that it's actually taller than it actually is, and the bottom of it is not flat. It tips slightly downwards to give that sense of floating. And you don't notice it when you're at any distance. You can only see that if you actually sort of put your head down on the steps and see that it actually sort of dips down. It's terribly clever. And and it's all beautifully proportioned along Pythagorean lines. And it's a very big place as well. It's an absolutely fabulous place. It's astonishingly beautiful, and it's amazing that even saw it was beautiful until I can't believe it. People were such, I don't know, just had no idea somehow. Well, how could they miss it? Anyway, and if you walk down below the Acropolis, you walk around the Agora, and you feel walking around without stopping. It's all a lot of fun. Anyway, which is just below the Acropolis. Anyway, so to go to Athens one day and enjoy the feeling. There'll be quite a lot of it left. Anyway, so there were all these Greeks, and yeah, we're talking. I've got Aristotle's dates somewhere. I can tell you when Aristotle lived. He was, oh, no, I haven't got it written down there. I'm sure I have written it down somewhere. Well, between the 5th and the 4th centuries, yes, was Aristotle. But there were various other Greeks. Of course, Euclid was the great geometer. He more or less he developed geometry in a way, and we tend to think of that, and I hope that at school you probably learned Euclidean geometry, named after Euclid, who followed Pythagoras into geometry and worked out all sorts of positive circles and all that. And Euclidean geometry also dominated. So I say it wasn't just one person; it was a number of them. Greeks worked out quite a number of things. One of the things they knew perfectly well, for instance, that the world was round. I mean, there's some strange myth going around that Columbus was the first person to work out the world was round. Right. He knew perfectly well the world was round. Everybody knew perfectly well the world was round. I told you last time, that people had all these sort of ideas of sort of non-concentric spheres and things about the land and water. You remember I was telling you last time, which seemed perfectly logical to them. Even doesn't seem in the slightest bit logical to us. One of the Greeks did a remarkable thing. He worked out, not only did he work out that he know that the world was round, but he worked out the circumference of the world. And he worked it out in a very, very clever way. He was called Eratosthenes. And the Greek Empire extended over quite a bit of the area of the Mediterranean around, and included Alexandria, which of course is on the Nile Delta. And what he did was he went south in Egypt, as you do, going up the Nile. And you go south, and you go south, and you go south. And he got to what we would now call Aswan. Have any of you been to Egypt? Have you seen Aswan? And we went up the Nile? We went up the Nile a bit. You must have gone up the Nile a bit. There's nowhere else to go in Egypt. Oh, there are.
Still counts.
Yeah, it doesn't count at all. That's not Egypt. That's Sinai. Yeah. Pretty good. At least you got that. I've never been either to Egypt, but anyway, you'll know that Egypt's quite it's quite a distance from the north of Egypt to the south of Egypt. Aswan is right down in the south. It's quite near the Sudanese border. And the Aswan Dam, the famous Aswan Dam, actually straddles the border between Egypt and Sudan. The dam itself is in Egypt, of course, and then the water builds up, but it goes across the border. The water hasn't worked out that there's a political boundary there, which is a bit irresponsible of it. Mind you, you'd thought the Egyptians might have noticed that too, that if they made a big high dam, that the water might spill over into some neighbouring hostile country. But anyway, they didn't seem to work that one out either. But anyway, the Lake Aswan, the Lake Nasser as it's called, goes into northern Sudan. Anyway, the point is, Eratosthenes went down there, and what he saw was really clever. Because on Midsummer's Day, what he saw was that when he stood up at Aswan, as what's now called Aswan, I can't remember the old name, but I think it was Aswan, he found that there was no shadow. There was no shadow of him at all down. So he did it with a stick, which of course would be rather better, because that's just a very simple object. He stuck a stick, made it absolutely vertical, and could see that there was no shadow in Midsummer's Day. Fundamentally, it's on what we would call the tropic line. But in Alexandria, on Midsummer's Day, there was a shadow. And he measured the length of it from the same pole, from exactly the same height. And he worked out what the shadow was. And having done that very, very carefully, he then realised worked out how far he'd gone between Alexandria, what we would call Alexandria and Aswan, worked out how far that was, saw how far his shadow had moved, and made him work out what the circumference of the world was. But what's more, although Greek measurements were not very precise, I mean, to be honest, I may have slightly advocated feet and inches and such things because we carry them around, but the very fact that I carry around an inch or a foot, and so do you, but if you're much smaller than me, your inch might be a bit smaller than mine. If you're much bigger than me, your inch might be bigger than mine. You see what I mean? It wasn't a desperately precise measurement. It was good, but not totally precise. And the Greek measurements were a bit the same. They weren't that precise. But as far as we can tell from Greek measurements, he got it really pretty well right. Do you know what the circumference of the Earth is? Roughly. Any idea at all?
From that way to that way.
What's the difference?
This way's longer.
Why is it longer?
Because the Earth is like yes, it's a sphere, but it's flatter.
Absolutely right. Yeah, well done. Yeah, no, she's absolutely right. Except for the fact that, of course, if you go this way, it's also going around the equator, so you still have to bulge out.
Yeah.
The equator bulges. Have I told you that? Wonderful pub quiz question, I think. Have I told you this? I told some of you, I think. I haven't told you all. What is the point on the Earth that is furthest away from the middle of the Earth? There's one obvious answer, and of course that one's wrong. Otherwise I wouldn't have asked the question. Well, what's the obvious answer? Yeah, top of Everest is the obvious answer, but it's wrong. And very interestingly, it is wrong. And it's wrong because of exactly what you just said, about that the Earth bulges in the middle. And the Himalayas are just far enough north, it was catch it with, but not very much of the bulge. The answer is Mount Chimborazo. Now, you may even not have heard of Mount Chimborazo, but the answer is Mount Chimborazo, which is in Ecuador, whose name gives away as to what latitude it is on. It's on the Equator. And the point is that Chimborazo is on the equator. It's only about 21,000 feet high, but the extra 8,000 feet or so is more, it more than compensates for that by the fact that the equator is that much further away from the centre of the Earth. So actually, the point on the Earth, which is furthest away from the centre of the Earth, is Mount Chimborazo in Ecuador. Now, there's a good thing that your parents didn't know. And you can tell me, I was delighted to discover that. Anyway, but what's the circumference of the Earth? It doesn't actually make all that much difference, although you're right, but it doesn't make all that much difference. Do you know roughly what the circumference of the Earth is? Sorry?
24,000.
Exactly. That's right, roughly right. 24,000 miles. And he hasn't got a computer in front of him. No, he hasn't. It's about 24,000 miles. I mean, and Eratosthenes wasn't far out. We know that he said that I say, judging by his calculations, we can't tell exactly, but he was certainly more than 20,000. We reckon probably 21, 22,000 at the very least, and probably up to about 25,000. He really was pretty good.
How do you spell the name of this guy?
Well, exactly. Do you think I should dare?
There isn't a sign telling you not to.
Sorry?
There isn't a sign telling you not to.
Is there?
We paid for it, so...
Yeah.
We paid for it, so...
There's nothing saying don't write on the wall.
But I haven't got anywhere else to write, so I couldn't. But it's all very...
Yes. if Brooks was to know... Eratosthenes is the name of the ship. I hope I don't get into serious trouble. Eratosthenes then was a remarkable man, and working this out, you can see where his ideas came from, though. The idea that you can actually think about the world in this kind of way. And he worked this out as to roughly the circumference of the... and really got it pretty near right. So Eratosthenes was remarkable. There's another one, Thales of Miletus was another one. I won't write him up. In some ways, people said he was the kind of father as well, because he was another one who sort of in the Pythagorean school sort of worked out, and he said that the whole world could be described in material terms. We hadn't got that idea really ever before, and in fact, of course, for a long time after that, we hadn't sort of it didn't feature very strongly that idea that you could describe the world in that kind of a way. So it was momentous in many ways, as the Greeks so often were. So that's enough on the Greeks for the minute. Then what happened? There seemed to be a kind of... Romans weren't really interested in this kind of thing. They didn't really develop science in any way. They developed all sorts of other things, but they never developed the ideas about the world any more detail than the Greeks did. What was interesting about that is it seems then that it sort of went into abeyance. We went into what are often known as the Dark Ages. Now, the Dark Ages, I suppose almost anything from about the year 0, which you may know actually didn't exist. Did you know that we went straight from 1 BC to 1 AD? Do you know that? I know. It means that the new millennium actually started on the 1st of January 2001, not the 1st of January 2000. But everybody made a fuss about 2000 because suddenly you got a 2 in front of things when we weren't used to the idea and hadn't been for 1,000 years. No, the new millennium definitely started in 2001. the Dark Ages were dark as far as science is concerned, possibly. They weren't, of course, dark for all sorts of other ways. Lots of things happened during those Dark Ages. We developed all sorts of other things, but I think we can say that for science, not a great deal happened then for quite a lot of centuries, at least in Europe. But it was happening in one or two other parts of the world. And it's as if science sort of moved, it sort of shifted, really. It first shifted in many ways. It went east. The ideas went east. The ideas of the Greeks went east. And went to India. And India became quite a centre for what we would think of as some sort of scientific inquiry. And perhaps I'll just use this central panel and see if they can hopefully rub it all off there.
I think it helps we've all paid collectively 13 grand for this 3 hours, so go for it.
That does help, actually. That's a very good statistic. I'll use that one. Yes, you mathematise it. That's very good. I like it. Yeah.
Doesn't account for differences in the contact hours.
Because you're never going to spell these names unless I write them up. So, because they're all Indian names, and you're bound to get them all wrong. So, those are his dates. Okay, so 5th century to 6th century AD. Aryabhata, a name you've never heard of. And I'm actually not expecting you to remember these names. I can't remember themselves, even myself, as you can see. I've got the paper in front of me. Aryabhata, as an Indian, a mathematician and astronomer, and not only did he know that the world was round, but he was the first. He really genuinely was the first, about just over 1,000 years before Copernicus, to work out that actually it all made much more sense if the Earth went round the Sun rather than the Sun going round the Earth. Heliocentrism, the centre of the universe being the Sun, was not new in Copernicus's day. Aryabhata had worked it out about 1,000 years before. Which is, because 1543 is when Copernicus published his idea. We're talking about 500 and something with Aryabhata. So he'd worked that all out. Ramagupta, another Indian, he was a little bit later, 7th century. He made an astonishingly useful addition to our science. Because what he did, not only, well, he vaguely thought about gravitation. He didn't quite formulate it, and certainly that took Newton to formulate gravity, as you all know, watching apples falling from trees and all that kind of thing. But what Ramagupta did was he introduced zero. The idea of zero. Romans didn't have it. Nobody really had it before that. And it's the idea of zero, because the thing about the idea of zero, and the whole importance of the idea of zero, is that makes your number chain infinite. If you don't have a zero, you can't. You'll know how Roman numerals, it goes I, and then V, and then X, and then L, and then C, and then M, what have you. You run out of letters after a bit. You don't, I mean, I don't know whether you could write in Roman numerals, 1993. It's quite awkward if you start to do that. Putting a zero in, you can just add it all up. It sounds so simple. It sounds so simple, but of course it's a breakthrough. And so often, simple things are breakthroughs. And a simple idea like adding a zero made a huge difference to mathematics. So that's what Ramagupta did, and he put the zero in. And he invented Arabic numerals. And you've probably noticed the anomaly already. he invented Arabic numerals. I just told you he was Indian, not Arabic at all. The Arabs got it from the Indians. The Arabs got it from the Indians. They're not Arabic at all. They're Indian. But we always call them Arabic numerals, and we use Arabic numerals. Obviously, Arabic numerals is what we're used to, but actually they're Indian. The Indians got there first, and so yeah, and the Arabs borrowed them, and we borrowed them from the Arabs. Well, that's fine. We didn't get them from the Arabs. We thought that we'd done. The Arabs very sensibly took them up. Quite right too. Obviously, they're good. They work. And if they work, well, then you use them, don't you? It's the obvious thing to do. So that's what Brahma Gupta. Get the names. I even can't remember these names, but I'm usually quite good with those sorts of names. Just finally, amongst the Indians, Bhaskara said, don't even try to remember these names, but do remember that they were Indians and that the Indians took it up in those early Christian centuries, between about the 5th and the 10th century. Now, Bhaskara was a bit later, it was in the 12th century. And he actually was a great mathematician again, lots of trigonometry he worked out, and he, amazingly, worked out that the planetary orbits were actually, almost certainly at least, not circular. We tended to credit the great Johannes Kepler, one of the most attractive figures to come out of 17th century astronomy, physics, maths, whatever you want to call it. And Kepler did, and Kepler did work it out independently. This man did it 4 centuries before. They were pretty good, those Indians. They managed to get quite a long way with all this. And he worked out, I say, taking on really the heliocentric model and working out that there's planetary. I mean, I don't know whether you knew this, but the planets don't go circular. We don't go circular around the sun. And you know, one of the reasons why we get climatic differences and things is because the ellipse and it moves slightly. You've got what's known as the precession of the equinoxes. You know, it's because the elliptical orbit around the sun, if I can exaggerate it, there's the sun. You know, you get closer to the sun, then you get further away from the sun, and then that moves. You know, sometimes you get further away from the sun and closer to the sun in the summer or the winter, and so you know it matters as to how it goes, and so and it changes. So he worked out, old Bhaskara, he worked it out, and you could see that this was the way in which the planets actually orbited. It was not circular, it was elliptical. Something very much we associate with Kepler. That's the Indians. I'll give you a 2-minute thought.